Okay, so over to you, Pietro.
Let me start by thanking the organizers for inviting me to this seminar series. And in today's talk, I will discuss these two recent preprints that appeared on the archive last year, where we discussed this topic that we dubbed propagation of many-body localization in an Anderson insulator. So let me first start by acknowledging my collaborators, Maxime, who is my supervisor here at IST Austria, Alex, a former postdoc that recently moved into Dima Abanin's group in the University of Geneva, Christina, that was an intern during last summer here and whose work was very important for the last part of the talk in particular, and finally Dima Abani, who collaborated throughout the whole work. Okay, so let me sketch a brief outline. I would start by briefly introducing thermalization in isolated quantum many-body system and possible ways to avoid it, and in particular focus on disorder system and on many-body localization. Then I would move to the competition of many-body localized systems with small thermal systems and try to prospect possible outcomes and sketch some of the theoretical and experimental approaches. And then I will dive in our proper contribution to this topic by first introducing some approximations that we took to tackle this problem, followed by full interacting tensor network analysis of both the dynamics and eigenstates. And finally, I would introduce our phenomenology of this system that, as I told you, we call propagation of MBL. And I hope it will be clear towards the end of the talk why this name. All right. So in the last decades, the technological advantage led to the possibility of studying so-called what we call artificial matter, so systems where the true lattice that we would have in our usual condensed matter is replaced by some laser trap, and this has a lot of advantages because in these systems the parameters of the Hamiltonian are highly tunable, and this allows to study, for instance, exotic phases of matter or some interesting non-equilibrium dynamics as in the quench experiments. And it also raises the question of thermalization or lack thereof in isolated quantum systems. So we are usually taught that systems thermalize where they interact with a microscopic path that allows them to reach the thermal equilibrium. But if the system, like here, the system S, is isolated from its environment, then how does it thermalize? And in addition to that, the system evolves with Hamiltonian dynamics, and hence, if we initialize the system in a pure state, it will remain such under the time evolution. And the answer of how the system reaches thermal equilibrium comes from let's say, dividing the whole system S into subsystems, like in this case A and B, and the system B would act as a thermal bath for the subsystem A, and thus subsystem A would thermalize according to usual quantum mechanical rules. And these can be formalized in using the eigenstate thermalization hypothesis that, in a very crude way, states that thermal eigenstates of a thermal Hamiltonian can be seen as approximately as random vectors in the Hilbert space, except of course they carry more information because they carry all the information about possible constraints that might be in the Hamiltonian, of course, energy conservation, but maybe also particle conservations or whatever other symmetry the Hamiltonian might have. And the formal statement of ETH tells that basically expectation values of local operators are given by this diagonal part where these O bar is basically the thermal equilibrium value of the observable at the mean energy E, and the off-diagonal part decays exponentially with the entropy of that energy states, and thus decays exponentially fast with the system size. And this also tells us that expectation values of local observables in thermalizing systems are smooth functions of the energy, as you can see, for instance, in this plot that I took from this nice review on the issue of thermalization, where they show the behavior of the kinetical energy as a function of energy itself, which is a very smooth function. And the generic Hamiltonian that you might think of is typically thermalizing, and that means the typical isolated system thermalize usually quickly under their dynamics, and this has many interesting consequences, and in particular, this means that observables reach their equilibrium value during the time evolution, and therefore the outcome of the dynamics is basically given by rules of statistical mechanics. In addition to that, eigenstates of thermal Hamiltonians have volume law entanglement. So it might be the case that we want, for instance, to store some information in an isolated quantum system, and we would love to get that information after some time. And if the system thermalizes, of course, there is no local observable that can keep track of the initial information, then we are interested in ways to avoid thermalization. And the answer to the question that if there are ways to thermalize, to avoid thermalization is yes, otherwise we wouldn't be here now. And among these ways, here I basically sketched two possibilities. One is integrable models, where basically the Hamiltonian has an extensive number of conserved quantities and hence avoids thermalization. But these models are usually very fine-tuned and unstable to perturbations, hence they do not provide a general way to avoid thermalization. And another possibility instead is adding disorder to the system, as in the case, for instance, of Anderson localization that is known from the late 50s with the groundbreaking paper of Anderson, where basically normal tight binding coupling was considered in addition with a random local potential epsilon drawn from some distribution between some minus W and W, where W sets the strength of the disorder. And this is known that a single particle in this Hamiltonian would localize exponentially close to its initial position. And hence, this, of course, breaks all possible transport in the system and therefore thermalization. However, the Anderson insulator is still non-interacting phase, and we need to study what happens to it when we add the interaction, and this is what has been called many-body localization. So to the previous Hamiltonian, one would add an interaction term of strength U, and if the system remains localized, then the initial local degrees of freedom, such as the particles or spins, depending on the system that we are considering, can be basically rotated through some quasi-local unitary into what have been called local integrals of motions, or LIAMs, which are this stressed version of the initial degrees of freedom. And in these spaces, the MBL Hamiltonian can be diagonalized, and it assumes this form here, where the coupling terms decay exponentially with distance among the LIAMs here. And although recently the very existence of MBL has been put in doubt, there are, however, several evidence of its existence, at least in finite systems that come from numerics and also from experimental studies, together with the mathematical proof by John Imrie that shows that in 1D and at least in one particular case, MBL exists and these unitary rotations do exist. So the consequences of many-body localization are several, and here I highlight a few of them. And among these, there is the memory of the initial configuration. So as I told you before, if we imagine to store some local information in a system that is many-body localized, then this information will be still available at later times. Then eigenstates of many-body localized Hamiltonian have RLO entanglement, and the dynamics grows entanglement entropy very slowly and just logarithmically. So I kind of presented to you these two paradigmatic ways of behaviors of isolated quantum systems, and then a natural question arises, which is what happens when the two of them interact with one another. And of course, when the thermal system is extensively large, then it would easily delocalize the previously localized system. So here we focus on the case where the thermal system is small, or more or less of the same size of the localized one. And we can identify two possible outcomes, either the, so let's say, melting of the localization, or the opposite case, which would be the freezing of the bath that was introduced by Rahul Nandkishore as MBL proximity effect. And so here I would like to explain a bit more what I mean by these. So if in the melting of MBL case, the previously many-body localized system interacting with the bath would basically allow two different configurations of Lyons with Lyons localized in different locations to become resonant with one another. And if this is happens extensively in the system, then eigenstates would be configurations where the Lyons are basically almost everywhere in the system, and this would hence destroy localization. On the other hand, the freezing of the bath happens in the case where the presence of localization basically is induced by the interaction to the bath itself, and then in some particular cases this can lead to the localization of the bath. And this has been approached both in theory and in experiments, and identified two, let's say, main approaches to this topic. The approach where the two systems are modeled by different particle species. So there would be particle species that interacts with the random potential and is localized, and another one that is free or translational invariant. And the two interact locally with some interaction, as depicted in this figure here. And this, since the thermal system here is composed by particles or degrees of freedom that have notion of locality, the back action of the localized system can lead to the localization of the bath, and therefore there could be the MBL proximity effects in these cases. Different direction is given by the case where the two systems are modeled by different lattice regions. So there would be a big part of the system that is localized, as in this paper by David Luiz, and another part of the system that is modeled as a ETH like Hamiltonian, and that interacts with all the rest of the localized chain with some long-range exponentially decaying coupling. And in this case, although the thermal system cannot be localized by the interaction with the disordered chain, it has been shown that if the disorder is small enough, a very small thermal system can lead to the delocalization of very large chains. And these two setups are also realized in experiments. And so these different lattice regions are realized in this experiment by Julian Leonard and his collaborators, where they basically took a one-dimensional chain called rubidium atoms and applied the random potential only on a portion of this chain of length LDs, while on the rest of the system there is no random potential applied. And they studied the behavior of localization and its stability depending on the on the dimension of this clean portion of the system. And what they found out is that if this clean portion is as big as half of the whole system, then they would observe signs of avalanches induced delocalization in the localized part of the chain. On the opposite side, there is this other approach of different particle species, where on a two-dimensional lattice here, with the same rubidium atoms, they use the two hyperfine states of the atoms to tune them in such a way that what they call dirty components atom would interact with the random potential, and the clean component would still be translational invariant. And again, they studied the localization of the dirty component as the density, as the number of these clean component atoms would increase. And what they found out, studying the imbalance, which is a commonly used experimental probe that basically measures the memory of the initial condition, they found out that when the number of these clean particles is very large, the imbalance rapidly decays to zero, and hence the dirty particles would delocalize. But still there is a value, like in this case NC equals 20, where even at late times imbalance has a finite value, and it seems that to be saturating and therefore not to decay anymore at later times. So the outcome of these experiments all focused mainly on the fate of the dirty component and on the possible delocalization of them. And the question naturally arises, that is, what happens instead to the clean component? Would they localize, or would they still be delocalized? And this is what we focused mainly in these two works. And we decided to follow the path of this different particle species approach, introducing this Hamiltonian, where the D operators would create or annihilate these disordered hardcore bosons, and the C one instead, what we call clean, which is basically by itself translational invariant. And then the two interact with the density-density interaction of coupling strength U. And we decided to study, let's say, initial states that are typically of this form. So the D bosons are arranged in such a way that they form a density wave pattern of distance 1 over nu D, where nu D is the average density of the D bosons. And on top of that, we add a single clean particle in the center of the system. So there is one single clean particle interacting with a large number of disordered bosons. And given the fact that we have two different particle species, the Hilbert space dimension scales very quickly with the system size, and that limits a lot the available system sizes that can be studied through exact diagonalization. And that's why we had to research on tensor network techniques to reach large system sizes to study this problem. But before I go into the full tensor network analysis, let me start by introducing some approximations that we use to understand the range of parameters that would be interesting to study. And first of all, we wanted to study the back action of the localized systems on the clean boson. And in order to do so, we an Hartree-Fock type approximation where we replace the density operator for the D bosons with its infinite time average that is given by this formula here. And this is justified if we consider that the dynamics of the D bosons is way faster than the one of the clean particle. And this would happen in the case where both the D boson hopping and the disorder are much larger than the clean particle hopping. And if we replace with this mean field type of approximation, we would observe that basically the clean particle interacts with this effective potential, which is distributed according to some distribution, which is of course between 0 and 1. And what we observe is that at weak disorder, so you can see here that disorder is equal to, for this blue line, this distribution would be approximately Gaussian and would be centered around the equilibrium value of the density, nu d. But however, when we increase disorder, we would observe that this distribution would change a lot and become strong disorder values, sort of bimodal with two peaks at 0 and 1. And this is easily understood if we consider the infinite disorder case, where the value of the infinite time average of the D boson's density can be either 0 or 1. And of course, when we have some finite disorder, that would be approximately the case, and therefore we would have this doubly peaked distribution. So this suggests that there is some sort of effective disorder acting on the clean particle in this limit. And in order to get a more clear understanding of it, we needed to take away from this distribution all the deterministic part of it. And in order to do so, we Fourier transformed the infinite time average and D, and removed from the Fourier transform a weighted contribution of the harmonics corresponding to the density wave pattern that we had in the initial state, and then transform back to the real space. And in this way, we obtain this effective disorder epsilon tilde that now is distributed between -1 and 1. And this is the result of such series of steps that would give this nice Gaussian distributed disorder with standard deviation that we call W tilde, that basically sets the effective disorder strength. And since the clean particle in this approximation interacts with an effectively random potential, and this in this approximation non-interacting, it is known that in one dimension, that is our case, it would be Anderson localized for all values of effective disorder. And using transfer matrix approach, one can obtain the localization length for this clean particle, and realize that in the weak disorder case, this is proportional to the inverse square of the effective disorder strength. And so if we analyze numerically this effective disorder as a function of the Anderson disorder W, we would observe that it is highly non-monotonic. And this is readily explained again by the fact that when the Anderson disorder is 0, the D bosons can spread basically freely through the system, and therefore they would not give any disorder. And as well as when the Anderson disorder goes to infinity, the D bosons would be again exactly localized with values 0 and 1, and therefore they would not induce any disorder on the clean particle. And of course, this non-monotonic.
Can I ask a question?
Yeah, sure.
I probably just missed why, but can you explain why again? Can you explain why at infinite disorder you don't expect, at infinite real disorder, you don't expect the D bosons to act as disorder? Because I would have thought, maybe you tell me what is wrong in my thinking, but I would have thought they're just localized at certain points, And then via the interaction, basically you have a disorder that is U or mine, or zero, depending on what the C particle will feel U or zero depending on where it is. So that's extremely bimodal disorder, right?
It would be in the case where we consider the d bosons distributed like randomly, but in this case we consider d bosons always distributed in a density wave pattern. Hence, it would actually correspond to some sort of lattice structure, actually, not anymore to random disorder. Is that clear? Okay.
Thank you. Yes.
So this non-monotonic behavior of the effective disorder is reflected in the localization length, and in particular, so these are results from numerics, and we see that the scaling of the localization length by the square of the interaction strength leads to a very nice collapse. So this confirms that that this is what happens in the approximate model. And in particular, I would like to stress here that the clean particle localization length can have very large values compared to the d bosons localization length that is of order 1, that there is a strong disorder, while when the coupling is very small, the clean particle localization length can be of order 100 sites. Okay, so these, however, as I said, an approximation, and particularly it overestimates localization, and we would want to go a step beyond. And in order to do so, we introduce two-body resonances, and thus when thus the interaction in these taking into account two-body resonances lead to the delocalization of the whole system. So we move to the Anderson orbital spaces, where the interaction can be seen as basically a hopping between localized state with a hopping parameter V alpha, beta, gamma, delta that is given by basically the overlap of the localized wave functions. And comparing this hopping strength with the typical level spacing delta E of the states connected by this hopping, we would obtain a ratio R that can be computed to be this formula that I show here, and localization is unstable whenever this ratio is larger than 1, and on the other hand, it would be stable when it's smaller than 1. So we computed this ratio numerically and obtained these curves here with, you see, interaction strength going from 0.5 for this dark blue curve to 5 for the orange curve down here. And by taking the intercept with r equal 1, we obtain this approximate phase diagram that predicts the presence of many-body localization, a strong interaction and some coupling, and strong disorder, sorry, and thermalization instead when both interaction and coupling and disorder are small. So for this region, we decided to study the region of strong interaction and strong disorder, where we expect to be many-body localization. And we first attempted with this again with the approximate approach to the dynamics. And here I stress that the interaction strength is very large, is 12, and the disorder is 6.5, and both hopping parameters are set to 1 in this case. So we use this time-dependent Hartree-Fock approximation that basically updates at each time step the potential that is the local potential felt that by each of the particle species, and this is done somehow self-consistently. So the potential felt by the d bosons would be, of course, the initial quench random disorder, and in addition to that, the expectation value at time t of the density of the clean particle obtained through this Hamiltonian, considering the interaction HC, which again is given by this potential epsilon c that is given by the time expectation value of the density of the d bosons obtained through the other interaction. So in this way, somehow we keep updating both interactions with the outcome of the other one. And so this is, of course, an approximate approach, and in particular, it neglects any sort of entanglement that can develop between the two particle species. However, it's very fast and allows to study large systems. And indeed, this is what we did next. And here I'm showing the density of the clean particle as a function of position x and of time. And as you can see, the outcome of these approximate dynamics is that the Xi boson behaves diffusively. So these red curves here correspond to square root of time behavior. And at late times here, it's completely delocalized and it reaches its thermal equilibrium value on a time scale that scales as the squared of the system size L. So then what happens to the D bosons can be already foreseen somehow, because the dynamics that remains of the clean particle after it reaches its equilibrium would be some fluctuations around the equilibrium value, and this would correspond in this scenario as some sort of noise on top of the Anderson insulator. And it is known that noise usually destabilizes localization, and this is indeed what we saw. So here I'm showing the density profile of the D bosons at a late time that, as you can see, shrank a lot. So the initial density wave structure is almost washed out at late times, and this can again be characterized also by the dynamics of the imbalance that at late times shows a very clear power law decay, and in particular by rescaling the time axis by the square of the system size, there is this very nice collapse that suggests that indeed once the clean particle has delocalized and hence on time scale scaling as square of the system size, the D bosons would start as well delocalized due to the fluctuations induced by the clean particle. So finally, we move to the sort of study of the full interacting system with quasi-exact methods of tensor network techniques, and in particular we used time-evolving-block-decimation, or TEBD, that basically consists of two steps. First, we need to trotterize the time evolution due into time steps of length delta t, and apply a layer of these gates at each time step. And after we apply the layer of gates, we need to perform a singular value decomposition to restore the initial MPS structure. And both these steps lead to some error sources, in particular the trotterization. So the fact that we split the continuous time evolution into steps of length delta t would contribute an error of order delta t to the fourth power when we use the Suzuki-Trotter decomposition, the fourth order Suzuki-Trotter decomposition. And then after we do each of the singular value decomposition, we need to keep a limited number of singular values, and this gives this truncation value at epsilon. That means that we discard all the singular values that are smaller than epsilon, and choosing with this choice of parameters, so delta t equals 0.05, epsilon equals 10 to the minus 9, and the bond dimension, meaning the maximum number of singular values that we are allowed to keep, of 3000, we obtain very reliable results in the dynamics. And so we evolve our initial state up to a time of 200 inverse hoppings, and we kept track of the dynamics of the density of both types of particles. And what we see is that the clean particle shows at each time an exponential decay. So here time would go from short times for the dark blue curves two long times where the curves are orange. And you would see that at each time, the clean particle is exponentially localized around its initial position with a decay length LC of t that is time dependent and tends to increase as time goes by. In particular, we also notice that so farther from the center than a certain parameter r of t, the density of the clean particle would decay faster than exponential, in particular would decay in a Gaussian way, and therefore we introduce these ansatz for the density of the clean particle that smoothly interpolates between an exponential and a Gaussian decay. So then what happens instead to the initially localized D bosons? And again, we study their density profile at late times, so at these 200 hopping times. And we observe that the density wave structure is well maintained at this late time. And in particular, there is no appreciable system size dependence, so the curves collapse on one another for all these system sizes from 30 to 60 sites. And the only effect that we can see from the presence of the clean particle is a slight enhancement of relaxation close to the center. So in this region here, the density wave would shrink a bit, but that's the only effect we see. And that we quantified also with the study of the imbalance. So the solid curves correspond to the full imbalance of the whole chain. And as you can see at late times, they all saturate to finite value, and they have this plateau behavior that can be characterized by the exponent beta here, that as you can see in the inset in the blue line, decays as system size increases and decays to zero. While if we focus on the central sites, so we take the imbalance, restricting ourselves to the central 6 sites, we would obtain this dashed line that collapse on one another for all the system sizes in a very nice way. And we observe that indeed there the imbalance is decaying a bit faster than with respect to the global one. And again, we characterize it by the exponent beta that is indeed larger than the one obtained for the global imbalance. So, as I told you before, we characterize the C boson density through these ansatz, and in particular, we wanted to study the behavior of this decay length, because of course it's of particular interest, because if it keeps growing, then the C boson would not localize. Well, however, if it saturates, it should be a good sign of localization of the clean particle. And what we did is that we kept track of this decay length LC of t for all the system sizes that we studied. And we added an additional system size of 15 sites where we could push the dynamics to much longer times. And what we observe is that indeed the decay length seems to saturate at late times. And we extracted through a fit the saturation value psi c for all the system sizes available. And we observed that as we increase the system size, this saturation value indeed doesn't change much. And hence we took this as some evidence of the localization of the clean particle in this system. And this happens, as I told you before, in the strong interaction case. And therefore, we also studied what happens when we decrease the interaction. And as you can see in this plot, the effect of decreasing the interaction is quite dramatic. And as we go to a small interaction of 2.5, the decay length would grow much faster than in the previous case. And again, if we obtain the saturation of this decay length through these dashed line feeds, we would see that at this weak interaction strength, it would be of 1 order of magnitude more than the system size, and therefore one could conclude that in this case the C boson is delocalized. But however, the effect on the D boson is not clear a priori what would happen even if the clean particle delocalizes. So are there any other non-trivial effects that we capture in this system? And to study that, we decided to go a bit further.
Sorry, can I ask a question on the previous slide? Yeah,
sure.
So it is, so in this left panel, the L equal to 30 and L equal to 48, I can't see these lines, but are they like fully overlapping with the blue line, or?
Yeah.
So you could really reach to the 10 to the 4 times for the whatever L equal to 48 then. So you can really see that they are leveling off.
Yeah.
Okay, so the green line is just under the blue line, then you're saying?
No, sorry. The green and the orange line are under the red line. So the main difference is mainly in the number of disorder realizations, and in the fact that the system sizes from 30 to 60 are obtained through the TEBD, while the system size L equal to 15 is obtained with some Krylov type of time evolution.
Okay, so then with TEBD, you could go up to time 100, basically.
Yeah, this is up to time 200, yes.
Okay, yes, okay, nice, thank you.
You're welcome. Okay, so we decided to investigate a bit deeper this system, and we first focused on connected correlation functions that, as you know, are just given by the usually 2-point correlators, to which we subtract the disconnected part. And assuming the localization, then assuming the Lyon's picture holds, one can obtain that in the infinite time limit, the absolute value of the average of the connected correlations should decay exponentially with the distance between the 2 points, and the decay length of this decay is given by the localization length of the D particles. However, at finite times, what we observe is that the connected correlations indeed decay exponentially, but with a time-dependent decay length LD of T, and we can keep track again of this decay length and compare the result that we obtain in the many-body localized phase, so when the interaction is strong, to the one obtained in the Anderson insulator case where there is no interaction at all. And as you can see in the Anderson insulator case, this D boson decay length saturates quickly to its finite value, that is simply the localization length, while in the MBL case, it keeps growing for some time, for some decades, until it effectively seems to saturate as well at late times. And again, we can obtain the saturation value xi through this fit that you can see maybe as the black dash line. And interestingly, this xi would be site dependent, and we would obtain through this to the study of the connected correlations a spatially resolved, so to say, image of the localization of the D bosons. And if we study that, then we would see that this D boson's localization length as a function of the site I is particularly enhanced in the center of the system, where the C boson is supposedly localized, while in its boundaries it has basically the same value as the Anderson insulator case. This tells us that the effect of the interaction basically leads to a relaxation of the D boson's localization length only in the center. So the effect of the interaction is really extremely non-homogeneous in this system, due, at least as we think, to the localization of the clean particle. And we studied this further through the entanglement entropy. So the non-entropy of reduced density matrix. And in this plot, I'm showing the entanglement profile S of X at some finite times t from 1 to 200. And we were initially a bit puzzled by this pattern that is quite unusual if you're from many-body localized systems, because there is this large sort of mountain of entanglement in the center, and the boundaries are completely non-entangled apparently. And so we ascribed this behavior to the fact that, as I told you, the interaction effectively is highly non-uniform due to the localization of the clean particle. And then we introduced this sort of phenomenological effective interaction U effective that is just given by the coupling strength U times our ansatz for the C boson density. And that at later times, this simply becomes some exponentially decaying function from the center of the system. And if we plug in this effective interaction into a sort of phenomenological formula for the entanglement entropy growth, we would obtain these dashed lines that are shown in the plot, and that have very good agreement with the numerical results. So this gave us the idea of this propagation of MBL, because what seems to happen here is that the fact is the clean particle gets localized due to the interaction with the disordered ones, leads to some very non-uniform growth of the entanglement, as if the many-body localized phase would propagate from the center where the clean particle is localized to the boundaries with a finite speed. And this can be observed also in entanglement dynamics. So here I'm showing the entanglement entropy as a function of time for different cuts in the system. So the purple line would correspond to the half chain cut, and here we see that entanglement starts growing logarithmically almost immediately. But as we go farther from the center, for instance, in the green and yellow lines, we can see that entanglement starts growing much later in time as we go farther from the center. And so we can obtain, so to say, the curve x of t at which entanglement starts growing logarithmically or start deviating from the Anderson insulator case. And we solve this equation for x, we would obtain this MBL propagation front, as we called it, x of MBL, that basically is proportional to the decay length of the clean particle. But however, it has a logarithmic growth additionally. So even if the clean particle effectively localizes with a finite saturation for this decay length, this MBL front would still keep growing logarithmically until eventually it would take the whole system, and the whole system will start growing entanglement logarithmically. And to further provide evidence for this, we showed in this right plot the difference between the entanglement entropy in position x at time t and the Anderson insulator plateau. And we see that indeed the system basically generates entanglement only within these red lines that correspond exactly to this MBL front that we obtained through our phenomenological approach. And so even if we add a single clean particle, the interactions still play a very fundamental role, and they change dramatically the behavior, for instance, of entanglement growth, but as well as correlations, as I showed you in the previous slides. So all of these, of course, is limited to finite times because it's dynamics and that's what we can do. And therefore we decided to try and go a bit further and add some other probes studying the behavior of eigenstates, of highly excited eigenstates of this Hamiltonian. And this was possible particularly thanks to the help of Christina, that, as I told you, was an intern last summer here at IST, and she, together with Alex, developed the version of the density matrix renormalization group for highly excited eigenstates, or DMRG-X. And what she did was to basically sample many eigenstates in the middle of the spectrum of our Hamiltonian and study the behavior of the clean particle density and of entanglement. So for each eigenstate, one can find the position I max where the C boson density is peaked, and then average among all the eigenstates around this position I max. And if we do so, we observe that the density profile that one obtains is again exponentially suppressed away from the position I max. And these localization lengths I see that depending on the range of the feet can be either this upper limit, the black dashed line, or the lower limit, the red one, is in very good agreement with the results we obtained in the dynamics. So these are good additional evidence for the localization of the clean particle due to the interaction with the disordered ones. And as well, studying in a similar way the entanglement entropy, we observed that in the boundaries or far from the position where the clean particle has localized, entanglement is very low and and has very low value, while as we get closer to the position where the clean particle is localized, there is this increase of the entanglement profile that is in agreement with this scenario of the propagation of MBL that I just described to you. And in addition to that, I would like to stress that what we observed also is that entanglement entropy, even doubling the system size from 30 to 60, doesn't show basically any increase as the system size is doubled, and hence that would also be evidence of many-body localization, because the eigenstates would still be RLO. So I hope that with this I sort of at least interested you in this system and in this phenomenology of the propagation of many-body localization. And with this, let me finish with some summary. So after introducing the topic of the competition of many-body localized and thermal systems, I showed you our perturbative arguments that predict the stability of MBL and of MBL proximity effect at strong interaction and strong disorder. Then I showed the results from both approximate and quasi-exact dynamics that and these latter sort of support the perturbative arguments, showing exponential decay of the density of the clean particle and stable localization of the disordered ones. And in addition to that, we provided some explanation for the unusual and interesting entanglement patterns that this model revealed, and through this phenomenological theory of the propagation of MBL, we are able to understand the behavior of entanglement and of correlations in this system. Of course, there remain many open questions. In particular, here I summarized two of them, which I think are the most interesting, and this would be the behavior of the system when we decrease interaction. So we saw that the decay length of the clean particle grows much faster, and then the question is whether the clean particle effectively delocalizes, or simply we have too small of a system size to understand what happens to it. And in addition to that, it's interesting to understand whether, even if it delocalizes, does it mean that the d bosons, the d particles, are delocalized as well? And finally, so far we focused on the simplest case where there is a single clean particle acting on the disordered ones. But of course, the goal would be to understand what happens in general, when we have a finite density of these clean particles. And of course, this is much more demanding on the computational side, but we are slowly trying to tackle this problem, and we hopefully will have a more clear understanding in the near future. And with this, I would like to thank you for your attention, and I would be happy to take any questions.
Okay, thank you very much for this great talk. So maybe we can stop the recording now.